So thanks everyone. It's amazing to be here, and thanks to Sang-Wan, my friend from MIT, inviting me. And I've been wanting to come visit KAIST for a long time because I've heard of so much great work that goes on here, and all the brilliant students and all the work that you do. So it's very exciting to be here. I'm also very excited to be in South Korea in general because of seeing the excitement and energy for AlphaGo and AI research and for the game of Go. So it's a real pleasure and honor to be here. So I wasn't expecting quite so many people. I was expecting it to be a normal academic lecture. So I'm going to talk to you today about really an overview of what DeepMind does. So, of course, I will talk about AlphaGo and give you some technical details, and you can ask me some questions about that. But then also I want to talk to you about the rest of the work that we're doing, because AlphaGo is very important. We have an amazing team on AlphaGo of about 15 people, but DeepMind is actually more than 200 people, so scientists. So actually it's only about 1/10 of the work we're doing at DeepMind. So let me start by saying, of course, AI is the science of trying to make machines smart. And I'm sure many of you are involved in AI and machine learning here. So DeepMind, as Sang-Wan said, was founded 2010, and we joined forces with Google in 2014. And we did that to try and turbocharge our mission to solve artificial intelligence. So how do we think about DeepMind? Well, we think about it as kind of like an Apollo program effort for AI. So as I said, there's more than 200 research scientists now. We're based in London, and we're growing all the time. But the other thing we're experimenting with at DeepMind is, so of course, we're experimenting on AI and trying to advance AI. But the other big experiment we're doing is on organization itself. How can we organize science more efficiently and more productively, but still make it very fun and collaborative? So what we've tried to do at DeepMind is try to combine the best of academia and how that should work in an ideal world with the best from the top Silicon Valley startups and how they operate. So from academia, we're taking blue sky thinking, ambitious thinking, interdisciplinary work, which I know is what, how KAIST works too. And then combine that with the energy and the focus and the buzz of the best Silicon Valley startups. And I think we've done a reasonably good job of that so far, and I think that's what gives us some of our unique edge. So at DeepMind, what is our mission? So we articulate it normally in 2 steps. So step 1, fundamentally solve intelligence. And then step 2, use it to try and solve everything else. So, we think that step 2 kind of follows on from step 1 in terms of what we can use general AI for. So how do we plan to do this? Well, we're interested in building general purpose learning algorithms. So these are algorithms that learn automatically from raw inputs. They're not pre-programmed or handcrafted in any way. So we're only interested in algorithms, building algorithms at DeepMind that can learn for themselves directly from raw data and raw experience. Secondly, we're interested in the idea of generality. So this is one system, a single system or a single set of algorithms that can operate across a wide range of tasks out of the box. Of course, we have an example of general purpose learning algorithms. It's up here, and the brain is the only example we have of that, but we know this is possible. So at DeepMind, we talk about this kind of AI as artificial general intelligence, AGI. And the hallmarks of AGI are that it's flexible and adaptive and potentially even inventive, and it's built from the ground up to deal gracefully with the unexpected. If we contrast that with what is mostly called AI these days, which we call narrow AI, usually that type of AI is handcrafted, so the solutions are directly programmed into the machine, and they're special case for a single task. And the problem with these kinds of systems is they're very brittle. So if something unexpected happens, they just break. They catastrophically fail. They have no way of dealing with something that the programmers didn't already cater for. So, of course, probably the most famous example still of this kind of narrow AI system is Deep Blue. As you all know, famously beat Garry Kasparov in 1997. But the thing about Deep Blue is that it couldn't do anything else. The systems and the program behind Deep Blue couldn't even be used to play a strictly simpler game. Like in the UK, we call it noughts and crosses. Very simple game you teach children. And even though Deep Blue had mastered chess, none of the programs and none of the knowledge it had would be useful for any other game, let alone any other type of domain outside of games. So I actually came away from this match. I remember this match very well. I was studying at Cambridge, and obviously with my chess background, I was following the match very closely. I actually came away more impressed by Garry Kasparov's mind than with the machine. Because obviously Kasparov could play chess at the same level as the machine, but also do many, many other things that we can all do. So Deep Blue was an immense technical achievement. Of course, it was a huge watershed moment in AI. But what we want to try and do is go beyond that. So the way we think about AI at DeepMind is through the glasses or the prism of reinforcement learning. And for those of so I know lots of you in the audience will know what reinforcement learning is, but for those of you who don't, I'll just explain it very quickly with this diagram. So if we think about intelligence with this kind of framework. So you start off with the agent system here on the left, and the agent finds itself in some kind of environment which is trying to achieve a goal. And that environment could be real-world environment, in which case the agent is a robot, or it could be a virtual environment, like a game, in which case the agent would be an avatar. And the agent only interacts with the environment in two ways. One way is that it gets observations about the environment through its sensory apparatus. So we mostly use vision for the moment, but we could use other sensory modalities, and we plan to in the future. And the key thing is that about the system is it only gets incomplete and noisy observations. It doesn't have perfect information about the environment out there. And the job of the agent system is twofold. One is to build as accurate a model as possible of the environment out there based on these noisy and incomplete observations, and update that in real time. And once it has that kind of model of the world, to then use that model to try and select the best action from the set of actions that are available to it at that moment in time that will get it best towards its goal, its overall goal. And once it's decided what to do, it outputs the action gets executed, and then that may or may not make a change to the environment, and then that drives a new observation. So all of this happens in sort of real time. Now, although this diagram looks very simple, it hides a huge amount of technical complexity, of course. And if we could solve everything to do with this diagram, then we know this would be enough for general intelligence. And the reason we know that is because this is how biological systems learn. So animals learn using reinforcement learning, and also in our human brains, we also use reinforcement learning as one of the learning techniques our own brains use. And we know this because some very famous experiments in the 90s, actually on monkeys, recording from single neurons, showed that the dopamine neurons actually code for prediction error. So that some of the neurons in our brain basically implement a form of reinforcement learning called TD learning. The second big principle we had at DeepMind was the idea of grounded cognition. So sometimes this is called embodied cognition. And this is the proposal that a true thinking machine has to be grounded ultimately in a rich sensory motor reality. So it's the only way you can get true grounded thinking. Now, normally, when people subscribe to this point of view, and maybe many of you here also agree with this, you start working on physical robots. Because, of course, physical robots are truly grounded in the real world and in a real data stream. But actually, the problem is, and I know there's a lot of robotics goes on here, and we love robots as an application, but they're quite fiddly to use. They're expensive, and they can be quite tricky on the hardware. So you can end up spending a lot of your time fixing the motors and the hardware and making the hardware work, and then less time you have to spend on the intelligence side, the software and the intelligence algorithms. And we wanted to focus, we were a small company when we started, and we wanted to focus on the intelligence question and the software side. And we didn't want to be distracted by hardware. So instead of that, partly because of my background making video games, we thought would be a really good idea to use games as a platform for developing and testing AI algorithms. Now, the games we've come to believe are a perfect platform for this for many reasons. Firstly, you can create unlimited training data by just running the game for longer. There's no testing bias. So one of the problems with AI development in the past has been that the people coming up with AI algorithms have also been the people designing the tests. And even if you try and be as objective as possible, you end up subconsciously designing tests that your algorithms are kind of well suited to. Of course, here, these games have been created by game designers and for other purposes, obviously to entertain people, not for testing AI algorithms. So we have to deal with real challenging problems. Obviously, in software agents, we can run many thousands, even millions of these agent systems in parallel to develop them. And games, often games have scores, which is quite a convenient way of measuring if your agent system is making incremental progress and becoming smarter. So we like using games as a testing platform, and it's one of the core things we do at DeepMind. So this comes to then the sort of the idea of end-to-end learning agents. And what we mean by that is starting with the raw inputs, so usually that's the pixels on the screen, and going all the way to deciding on an action, which is the whole intelligence stack. And we're interested in that entire problem set, all the way from perception to action. And in fact, we work on all of these different areas. So our big innovation, we call it deep reinforcement learning, is combining all of this together. So we want to combine deep learning with reinforcement learning. And this allows reinforcement learning to work at scale. So the first thing we tried this on was Atari games, and old classic Atari games from the 80s. So the reason we chose Atari is because it's the first sort of gaming platform that was really popular and that has hundreds of different games available for it. Now, what we combine the deep learning with the reinforcement learning to do is the deep learning does the perceptual processing, and then the reinforcement learning effectively does the decision making. So I'm going to roll a few videos now, and before I do, I just want to explain to you what it is you're going to see. So the agents only get the raw pixels as inputs. So there's 30,000 numbers coming in per frame, because the Atari screens are 200 by 150 pixels in size. And the goal here is simply to maximize the score. The agents learn everything else from scratch. They're not told what they're controlling, what gets them scores, what the rules of the game. All of that they have to learn from first principles. So they don't even know, for example, that pixels next to each other are correlated in time in a video stream. It has to learn all that structure for itself. And then there's the idea of generality again, which is a single system to play all the different games, at the same single system with the same hyperparameter settings. So the first video I'm going to show you is the iconic game Space Invaders. So if you're as old as me, you'll remember this game from the 80s. And initially, I'm just going to roll the video now. At the beginning, before the agent has had any training, it's just trying random things. So it's controlling the green rocket at the bottom of the screen, and it's losing its 3 lives immediately, because obviously it has no idea even what it's controlling, let alone what it should be doing. But then if you leave the program playing the game overnight, for about 20 hours. You come back the next day, and now it's superhuman level at playing the game. So every bullet it fires will hit one of the Space Invaders. You'll see it's learned the pink mothership that comes across at the top of the screen in a minute is worth the most points. So it does these amazingly accurate shots to do that. And if you remember at Space Invaders, they get faster as there's less of them. So just watch very carefully the last shot, and you'll see that it's predicting where the Space Invader will be. So it's very cool. So you can see it's built a very accurate model of this data stream that it's seeing. So I'm going to show you a second video now, which is Breakout. It's my favorite Atari video. And I'm going to show you more gradations of the agent getting slowly better over time. So in this game, you control the bat at the bottom of the screen, the bat and ball, and you're trying to break through this rainbow-colored wall brick by brick. So you can see the agent here is, after 100 games, it's not very good. It's missing the ball, but it's starting to get the idea it needs to move the bat towards the ball. So now after 300 games, now the agent is getting the ball back almost all the time, even very fast angles, which better than humans can do this. So then we thought, that's pretty good, but let's leave it for another 200 games. So we played 500 games now. And then it discovered, to our surprise, the optimal strategy was to dig a tunnel around the side and then put the ball to the back, which is amazing accuracy. And so this is the optimal strategy that it invented. And what's very funny is that the designers, the researchers and engineers, they're brilliant engineers and researchers who built this system called DQN, but they're not so good at playing Atari games. So they didn't even know that strategy. So they were taught something by the agent system. So this agent, which we call DQN, Deep Q Network, is really a general agent for Atari, of course, only for Atari games, but within the domain of Atari games, it really is a general artificial intelligence. So here I'm going to run a medley of different games just very quickly, and you'll see the same agent can play all these very different games, fighter pilot games, one of the very early 3D games, and you can see all of these games have very different rules. Of course, the classic Pong, it's controlling the green bat, it always wins 21-0. Then submarine games, many different games, really different ones. And the boxing controls the left-hand boxer. It does some sparring, and then it gets the inbuilt AI to the side, and then it just gets infinite points to win. So it's just worked out how to exploit the system. So this is the first time really that there's been any a kind of general agent that can start with raw experience, raw data, and for itself learn through trial and error, learn from its mistakes, and master quite a challenging set of problems, these Atari games. And if you're interested in this work, you can see it in our first Nature paper last year, front cover, that we also released the code. So you can play around with DQN yourselves if you want and apply it to your problems. It's all on the Nature site. So then we moved on from Atari games and 2D games, and now we're working on 3D games. We work on robot simulators. Eventually we'll work on real robots. And of course, as you know, we've been working on Go as well, which I'll talk about in a bit. So here is the same system now working on some 3D games. So we tried it in a driving game, and it again, just from the raw pixel inputs, it's learned how to drive around a racetrack and overtake cars, drive around 200 kilometers an hour, and do some quite cool overtaking maneuvers that we'll see in a second. So, and again, just from the pixels on the screen, there's no other input. It learns how to drive cars. It can also, we're now up to the games in the late 90s, so we're using the Quake engine, and we use it to create maze problems, 3D maze problems. And our agent can find rewards like these apples in the maze, and then remember how the maze works and find its way out of the maze to the exit, all just from the pixel inputs. So, of course, now we're making more and more complex and sophisticated 3D environments, and we'll be publishing more work on that later this year.